last but not least, we want to recap everything we learned about hypothesis testing for the difference in two samples or difference in two populations. Excuse me. So we had three sections that touched on this: 11.1, 11.2, and 11.3. Now, where these hypothesis tests are located is in the notes packet. It might change from semester to semester. The current semester I have, it's 330, 331, and 332. Excuse me, 331, 332, 333. So 11.1 is 331, 11.2 is 332, 11.3 is 333. Now 11.1 is about the difference in independent proportions. Dependent proportions is actually more difficult. We would do that in chapter 12. Dependent means, which is actually the simplest of the three, because you find the differences and then construct a hypothesis test on those differences. And then independent means. All right, now step 3 is from the calculator for two of these, and that's because if I go grab step 3, that is the formula where p hat is equal to that formula, and that's just annoying. So we're just going to use the calculator instead. So we're just going to use the calculator for that. And similar to T0, let me go grab that page from page 333 for me. There we have it right there. So there's T0. It's just tricky to put in correctly all the time. There's a lot of order of operations to keep track of, and it's just easier if we just use a calculator. We paid good money for it, so we might as well use it. The one that we can do by hand still is 11.2, because 11.2 is really more of a chapter 10 problem, because let me pull up the chapter 10 formula for you. There, if we look at chapter 10, section 10.3, you see T0 is x bar minus mu 0 over s over the square root of n. That's basically the same thing as this. It's just that mu 0 is always hypothesized to be 0. You always assume there's no difference in the groups unless you can prove otherwise. So you have d bar over sd over the square root of n. Technically, when you get into other upper level statistics courses, you actually can hypothesize a difference for mu d, but our book always assumed 0. All right, now what parameter are we hypothesizing about in our null hypothesis? Well, in the 11.1 section, we're hypothesizing a difference in the proportions. We're assuming that the proportions for the two groups is different in this particular way, right? And the statistic we use to test that is P1 hat minus P2 hat. Right, so we're using the difference in the sample proportions to test the difference in the population proportions, but we're using our calculator to do it because the formula, again, is just horrendous. We don't want any part of that formula. All right, now what about the difference in independent means? Let's do 11.3. Well, by the same token, it's x bar 1 minus x bar 2. So we use the sample difference in between those two samples. So we take the mean of one sample, the mean of the other sample, and we find the difference between those two, and we're using that to test what we thought the difference in the population values was. Again, that leads us to the simplest one in a way, which is the difference one. And that's where we use d bar, which is the mean of the differences. So this is the mean of all the differences, sample mean, as opposed to the mean of each of the different samples. So let me write that down. And this is the difference of the sample means. They're not the same thing. For 11.2, you actually find the differences first because they're matched pairs, and then find the mean of that. For 11.3, you find each of them separately because they're independent. So you find their means and then compare the two. And of course, 11.1 is different anyway because 11.1 is about proportions. So that's the difference in sample proportions. So using that difference in sample proportions to hypothesize what you think the difference in the population proportions is going to be. So in a way, 11.1 and 11.3 are kind of similar. 11.1 is talking about two independent samples, but it's the proportions for those two samples. So you could poll men and women and figure out, what percentage of them think such and such. So you'd have that difference in population proportions. Or you could have men and women take a test. What's the difference in their population means? That is 11.3, so two separate groups. 11.2 is the special case where they're actually like before and after, or husbands and wives, brothers and sisters, people that are related and not independent of each other. And that makes it kind of an easier case, but kind of a special case. All right, now the calculator entry for each of these is clearly labeled on the paper. So if you look at your appendix or your exam notes packet, you can see that I've highlighted what is the calculator entry in this kind of gray box on each of these sections. So it's a 2-SAMP t-test for 11.3, just a regular t-test for 11.2 because 11.2 actually works like chapter 10, and then a 2-prop z-test for 11.1. There we have those. Now the hardest part is actually figuring out what's being asked for. That can be the really tricky bit, especially with 11.2 and 11.3. So you want to try to figure out, are we talking about, well, first of all, hypothesis tests. So look for things about, does it ask you to do a test? And then look for, are we talking about proportions? Because if we're talking about two proportions, two groups and proportions, you're talking about an 11.1 problem. If you're talking about matched pairs grouping, then that's 11.2, or if they're independent means, then that's 11.3. All right, so for 11.1, the problem's going to ask you to do that hypothesis test, and you've got to look for two separate proportions given somewhere. It could be X and N are given to you. It could be percents are given to you. If they talk about, 70% for men, 80% for women, that kind of thing. Or if they give you the actual numbers. We polled 1,000 women and 800 of them thought this, and we polled 1,000 men and 700 of them thought this, then that is independent and it's talking about proportions. In which case, then the things you'd have to test are the same things you'd have to test to make a confidence interval. You need the sample to be random, you need them to be independent of each other, you need the samples to be independent of the population. Yet again, there's that classic, we kind of fake it if it's without replacement, with n being less than 0.05 capital N. You might have to talk about that a bit. And then we really want to check that both of the groups are normal, that n1 times p1 times 1 minus p1 and n2 times p2 times 1 minus p2 are both greater than or equal to 10. And again, all of that falls from section 8.2, the central limit theorem for proportions. All right, now what about for the difference? Well, the problem's going to ask you to perform a hypothesis test, but it's going to give you differences and a matched pairs sample somewhere. So you've really got to scope out whether it's that matched pairs type. Is it before and after, husbands and wives, people that are related, that kind of thing. That's a more matched pairs. You got to look for two sets that are completely interconnected. So that'll be honestly a little bit easier to spot just because matched pairs is something so special. And often we'll just give you the data set and ask you to find those differences and then conduct the test on those differences. There, those are in there. So you need to have a random sample. You need it to be a dependent sample, and then you need to know that your sample, even though it's dependent upon each other, the before and after, or husbands and wives, that kind of thing, but the sample is independent of the population still. So you need your n to be less than or equal to 0.05 capital N if you're sampling without replacement. And then it has to be normal. The sample has to be from a population that is normally distributed, and that's either given to you or a normal probability plot is given, or we use the rule of thumb that n is greater than or equal to 30. Now, the real trick can be telling the difference between the ones for means for a dependent sample and the means for independent samples. And the best thing to do is to look around and see, is this matched pairs? Are these groups forming perfect pairs? Or are they two separate data sets that really have no relationship in that way? If they are separate data sets that are independent of each other, that means they have independent samples. And if you're talking about the means or the standard deviations or that kind of thing, if you see means and standard deviations given to you in the problem, or if they give you two separate data sets, then that's a sign you're doing the difference of two sample means, in which case you'd have to check all the things you have to check pretty much for a single mean, but you have to double it. So you have to do it for each of those separate groups because they're independent. So you have to check both groups are bigger than 30 or both groups are normal if you're given two probability plots, normal probability plots. And then you have to check that they're both independent of the population. You have to check that they're independent of each other, all that good stuff. Now the distributions used are pretty obvious. The proportion one, as per usual, uses the z-distribution, and the two mean ones use the t-distribution, just like in chapters 9 and 10. Proportions used the z-distribution, means used the t-distribution. The only exception to that is the sample size formula from section 9.2. But everything else, means always use t, and proportions always use z. Now, how do we find the critical values? Well, we would need to know the degrees of freedom for this one over here on the right for 11.3. So we're actually kind of not going to bother with it for the most part. But we could find the other two because there's z alpha over 2 or plus z alpha or negative z alpha. So let me type that up. So there we have it. So the t-table is how we get, or the t inverse t function is how we get the t-distribution values for t alpha over 2, negative t alpha, positive t alpha. And the inverse norm, or the bottom row of the t-table, is how we come up with the z values. So negative z alpha, positive z alpha. Now remember, TT stands for two-tailed, LT is left-tailed, and RT is right-tailed. So the plus or minus z alpha over 2 is a two-tailed test, also the same as a confidence interval. And then negative z alpha is left-tailed, positive z alpha is right-tailed. So we would use inverse norm 0 and 1, right, for that part. Left tail area. Again, some of the new calculators will actually let you use something other than left tail area, but that's the one we've used. And then inverse t, left tail area for sure on that one. That has to be left tail area. Or the t-table. Your degrees of freedom on the matched pairs case is pretty simple. It's just n minus 1. So that's no trouble. So these two critical values you could find with no problem. 11.1 and 11.2's critical values. That leads us to, yet again, 11.3. 11.3 is a little weird. Technically, our book says to use the smaller degrees of freedom of n1 minus 1 and n2 minus 1. And I should have written that back in the earlier confidence interval table. Let me scroll back there. Right here, because you never know if the book is going to force you to do it for, let's say, a MyStatLab problem or something like that. So if you need to, you're going to use the smaller one. But in reality, we're going to use very rarely because real true DF is very hard to find. So we might not even be asked to do it hardly at all. There we go. All right, so we will only very sparingly ever have to do this. Might show up in a MyMathLab question or something like that. And our book has us just erring on the smaller side, erring on the side of the smaller degrees of freedom of n1 minus 1 and n2 minus 1, but that's kind of fudging it. The true degrees of freedom is a really horrendously large formula that we're not going to use. So in general, we're not going to find this critical value very often. We're just going to use our calculators and make it do the hard work for us. That's why we paid good money for it. And remember, you only have to do this step 4 critical value piece for the classical method anyway, and we don't do a lot of classical method from chapters 11 and 12. All right, we are all done with chapter 11. I'll see you back here for more lecture videos in chapter 12.